Hi viewers, I am Damodaran. Welcome to this video lecture. Four Square Theorem states that every positive integer can be written as a sum of squares of four integers. The history of the problem is quite interesting. The theorem is a starting point of world famous Waring's problem. Before stepping into the details of the proof, let us look at the origin of the problem. Arithmetica is the title of an ancient text on mathematics written by the Greek mathematician Diophantus in the 3rd century AD. It is a collection of algebraic problems giving numerical solutions of determinate equations and indeterminate equations. There were 13 volumes of Arithmetica. The Four Square Theorem was first proposed by the Diophantus of Alexandria in his treatise Arithmetica. It is believed that the proof was given by French mathematician Pierre de Fermat in the 17th century. However, he did not publish the proof. The theorem regained momentum when French mathematician Claude Gaspard-Bachet translated Arithmetica of Diophantus from Greek to Latin in 1621. In this period, he had conjectured Four Square Theorem, known as Bachet's conjecture. The right hand side picture which you are seeing is the first page of the book which he had translated from Greek to Latin. The classical theorem was proved by Joseph Louis Lagrange and published in 1770. This is the reason why the theorem is also known as Lagrange's theorem or Lagrange's Four Square Theorem. Later, German mathematician Adolf Hurwitz proved Four-Square Theorem using quaternions. There is another proof using Minkowski's theorem via lattices. In the same year, British mathematician Waring, who lived in 18th century, proposed a generalization of Four-Square Theorem known as Waring's problem. The proof of the Waring's problem was provided by German mathematician David Hilbert in 1909. Consequently, the theorem is referred as Hilbert-Waring theorem. There are many deductions of Waring's problem which are pursued by many mathematicians. Having known the fascinating history of Four-Square Theorem, let us venture into the details of the proof. The proof given by Adolf Hurwitz using quaternions is followed here. Four Square Theorem. In this session, we are going to see what is the statement and how to prove the Four Square Theorem. Look at the statement. Every positive integer can be expressed as a sum of squares of four integers. This is the statement. To prove this Four Square Theorem, we need to know some results from the previous chapters. So let us see what are those results. Prerequisites required for reading Four Square Theorem. First one is Wedderburn's theorem, which says every finite division ring is a commutative ring. We are going to make use of this. Then characterization of left ideals in Hurwitz's ring, which says for every left ideal L of the Hurwitz ring H, there exists an element U belongs to L such that every element in L is a left multiple of U. That is also required to prove Four Square Theorem. Third one, the usual first isomorphism theorem of rings. Then fourth one-to-one correspondence between the set of ideals of R by U and the set of ideals of R containing U. And finally, we need this result. If R is a ring with unit element not necessarily commutative, such that the only left ideals of R are 0 at R, then R is a division ring. Okay. So we will make use of these results wherever necessary. So let us go to the proof of Four Square Theorem now.
Okay. We will have to prove this theorem for every positive integer. We are going to take the first case, that when n is a prime number. So first we are going to prove the theorem when n is a prime number. Okay. When n is prime, there are two cases. Either it can be an even prime or it can be an odd prime. Okay. The only even prime number is 2, and we can easily see that 2 can be written as 1 square plus 1 square plus 0 square plus 0 square. Therefore 2 can be written as a sum of squares of 4 integers. Therefore the theorem is true if p is a even prime number. Now let us take the other case, that p is an odd prime number. So we are going to that case now here, when p is an odd prime number. Okay. Let Jp denote the ring of integers modulo p. That means if you take J3, it will consist of only 3 elements, 0, 1, 2. If you take J4, then there will be only 4 elements, 0, 1, 2 and 3. Okay. Now we are taking Wp as the ring of quaternions over Jp. That means Wp is defined like this. See, these coefficients alpha naught, alpha 1, alpha 2, alpha 3 are not general integers, but they are coming from the ring of integers. Okay, obviously in this there will be only p power 4 elements, because for alpha naught there are p possibilities starting from 0 to p minus 1. In the same way for alpha 1, alpha 2, alpha 3. So p into p into p into p 4 times. So p power 4 is the order of this. Therefore it is a finite ring. Okay. Right. Now we have taken p is an odd prime, therefore p is not equal to 2. In the Hurwitz ring, what is ij? Ij is equal to minus ji. Minus ji. This minus ji is not equal to ji because p is not equal to 2. What happens if p equal to 2? If p equal to 2, in Jp we know that minus 1 is the same as 1. That means minus ji will become ji, therefore this property is satisfied. But here, since minus 1 is not equal to 1, I cannot write minus ji is equal to ji. Therefore ij is not equal to ji, making Wp a non-commutative ring. That means it is not a commutative ring. Okay. See, Wp is already finite ring. It is not commutative ring. But what is the Wedderburn theorem says? Every finite division ring is a commutative ring. Now Wp is finite. Now suppose Wp is commutative, then what happens? We will get that Wp is not a division ring, because Wp is a division ring. Because it is finite, it will become a finite division ring. Therefore by Wedderburn's theorem it will become a commutative ring. But Wp is not commutative, therefore Wp is not a division ring. So that is, we are deducting this Wp is not a division ring from Wedderburn's theorem. Okay. Right. Now there is a result which I quoted in the pre-request. It says, what it says, if R is a ring with unit element, not necessarily commutative, such that the only left ideals of R are 0 and R, then R is a division ring. So that means if R is a division ring, there will be only two left ideals, 0, the singleton set, and R itself. But now Wp is not a division ring. That means this condition is not satisfied. That means apart from 0 and Wp has another left ideal. Okay, so from this result we get that Wp must have a left ideal which is neither 0 nor Wp. Okay, right. Now let us take a new set V defined as x0z plus x1i plus x2j plus x3k, where these are all integers, and more importantly p divides each of them. That means each of these coefficient is a multiple of p. Then it can be easily seen that this V is a two-sided ideal of the Hurwitz ring H. Okay. Now we are going to prove that H by V is isomorphic to WP. Right. Okay. Now we are going to prove this using first isomorphism theorem. Therefore, for that we are defining a map F from H to WP in such a way that if you take any A belongs to H, A equal to A0Z plus A1I plus A2J plus A3K belongs to H, then we are defining F of A as alpha naught plus alpha 1I plus alpha 2J plus alpha 3K, where these alphas are in JP along with the condition that AI and alpha I are congruent with respect to modulo P. This is true for I equal to 0, 1, 2, 3. Okay, that means these alphas are nothing but the remainder of A naught when divided, A naught, A1, A2, 3 when divided by P. Okay. By the definition of congruences, we can easily see that F is a ring homomorphism. Okay. Next, we are going to prove that F is on 2. So, we are taking this as subclaim 1. Okay. Means, let us start with element from the second set. Second set is WP. So, we are taking an element from there. Right. Now, for I equal to 0, 1, 2, 3, we are taking Bi as a representative integer of the class Bi in JP. That means we can actually take B naught equal to B naught, B1 equals B naught equal to B naught, beta naught, B1 equal to beta 1, B2 equal to beta 2, etc. Okay. When you take that, actually beta is congruent to Bi mod P because we are taking one and the same. Now we are forming a new element B with this B naught, etc. Okay, right? But here the coefficient we are writing as Z. Because of this and all these are integers, B belongs to H. B belongs to H, and of course f of B is equal to, as per our definition, we will get this is equal to beta naught Z, beta 1I, beta 2J, beta 3K, etc., which implies f of B is equal to beta. So for any element taken, beta taken from the second set WP, we have a pre-image B in the first set, making F is an onto map. Therefore, this subclaim 1 is proved. Okay, now we are going to the second subclaim, which is kernel of F is equal to V. So let us start with an element in the kernel. This is an element, X is an element in the kernel. What is the meaning of that? X is in the first set, which is H, and it goes to 0, so f of x is equal to 0. But how f of x is defined? Alpha naught plus alpha 1I plus alpha 2j plus alpha 3k. So that is equal to 0. Okay, if this is 0, automatically all coefficients are 0. Okay, alpha naught etc. is equal to 0. Okay, alpha naught is actually congruent to x naught. Okay, but alpha naught is 0. So xi is congruent to alpha I is 0. That means x naught is congruent to alpha naught, which is 0, x1 is congruent to alpha 1, which is 0, and so on. Okay. If an element is congruent to 0 mod p, that is equivalent to say that it is a multiple of p. Therefore, each of these xi is a multiple of p. Each of these xi is a multiple of p. Okay. Therefore, we are getting like this. Right. Which implies x is equal to this. You see, each coefficient is a multiple of V. That is the definition for the element to be in V. Therefore, this belongs to V. Okay. So, when you start with an element kernel of F, if x belongs to kernel of F, we prove that x belongs to V. You can also reverse. You can go in reverse direction. If you start with x belongs to V, you can prove that X belongs to kernel of F. Therefore, kernel of F is the same as V. So we proved our second subclaim. Okay. Now, by the first isomorphism theorem of rings, we have that H by V is isomorphic to WP because of subclaims 1 and 2. Okay. So we proved this claim that H by V is isomorphic to WP. Right. Now, by this isomorphism, we can come to a conclusion. Okay. Because these two are isomorphic. WP, we had observed already that WP satisfies a condition. What is the condition? It has a left ideal. It has a left ideal which is neither 0 nor H by V. This we already observed here. You can see here. We have written this. We have written here. You can see here. We must have a left ideal which is neither 0 nor WP. So that step only we are making use of here. Okay. WP has a left ideal which is neither 0 nor WP. So because there is a ideal which is neither 0 nor WP here, correspondingly we will have a ideal which is neither 0 nor H by V here. That is what we are writing here. See, H by V has an ideal which is neither 0 nor H by V. It follows because of this isomorphism. Okay. Now, because of this relation, V cannot be a maximal left ideal of H. Because there exists an ideal between 0 and H by V, V cannot be maximal left ideal. That means between V and H, there is a left ideal because V is not maximal. Therefore, there exists a left ideal between V and H. And this L is neither equal to V nor is equal to H. Okay. Now, another prerequisite I told you that characterization of left ideals means if you take any left ideal in Hurwitz ring, we can find an element U belongs to L such that every element in L is a left multiple of U. That we are applying here. By the characterization of left ideals of H, there exists an element U belongs to L such that every element in L is a left multiple of U. So it comes from that left characterization of left ideals. Okay. Right. Now, P belongs to V. Why P belongs to V? You see, what is V? V we have already taken as like this. We have taken already like this. Okay, V is a ideal. So definitely P will be in V. Okay, because P is in V, P belongs to L. Thus, there exists C belongs to H such that P can be written as CU. This is because every element in L can be written as a left multiple. Okay, this P belongs to V implies P belongs to L because V is a subset of it. Okay, right. Now we are going to see what about the inverse of C and inverse of U. In case C has inverse in H, then by multiplying C inverse on both sides, we will get that C inverse P equal to U. Okay. Now look at C inverse P. P belongs to V and V is a left ideal of H. C inverse belongs to H. Therefore, this product will be in V. Okay. But then this C inverse P is nothing but Q, which implies U belongs to V. Right. Okay. If U belongs to V, since every element of L is a left multiple of U, all the elements of L will be elements of V. Therefore, L is a subset of V. But already V is a subset of L. Therefore, L equal to V. but according to our choice, L is not equal to V. So this is a contradiction. This contradiction arises because we started with C as an inverse in H. That shows that C does not have an inverse in H. Well, if you have an element which is Hurwitz quaternion, which is not having inverse, then there is a result which says that n of C is greater than 1. N of any element in H is a positive integer. In addition, if that element is not having inverse, then n of C is greater than 1. Okay. Now, let us take the element U. Suppose U has inverse in H. That means U inverse belongs to H. That means this is in H and this is in L. Therefore, because L is a left ideal, it belongs to L, which implies 1 belongs to L. If an ideal has unit element, then it becomes the whole ring. Therefore, L is equal to H. Therefore, L is equal to H. So we get this. But then, by our choice, L is not equal to H. So again, this is a contradiction. Therefore, this contradicts this. That means U does not have an inverse in H. As before, because U is not having inverse in H, n of U is greater than 1. So we proved n of C greater than 1. Also, n of U greater than 1. Okay. Now, with this we proceed further. Since P is equal to Cu, n of P equal to n of C into n of P, because we know that n of xy is equal to n of x into n of y. What is n of P? P is an integer, so n of P is equal to P square and n of C equal to. Now from this you can see that already we know that n of C and n of U are greater than 1. So both of these numbers are greater than 1 and both of them divide P square. And there is only one possibility for this. That means both n of C and n of U must be equal to P. So both of them are P. Right. So with this we go to an important claim now. 4P is a sum of squares of 4 integers. Okay. So let us start with an element U belongs to H. Okay. Because it is in H, we can write in this format where the coefficients are integers. Now let us multiply 2 with that, then we will get this step. Okay. Remember Z is equal to half of 1 plus I plus J plus K, and multiplying these two and combining with corresponding terms, we will get this expression. M naught equal to M 2M1 plus M naught I plus 2M2 plus M naught J plus 2M3 plus M naught K. Getting this is easier, it's not difficult. Okay, now we take norm. When you take norm on both sides, left hand side is norm of 2u, whereas the right hand side, norm of this element is nothing but the square of each and every element. Okay, but what is n of 2u? N of 2u is n of 2 into n of u. N of 2 is n of alpha is alpha square, so n of 2 is 4, and n of u we already proved it is equal to p. It is already equal to p, right? Now this 4p we are getting like this. Look at the right hand side. We have 4 squares. All these numbers inside the bracket are integers. That means 4p is a sum of squares of 4 integers. That proves this claim. That proves this claim. Okay, right. Now with this we go to the next claim. This is a trick used by Euler. Let us see what it says. If 2a is equal to x0 square plus x1 square plus x2 square plus x3 square, where all these are integers, then a is equal to squares of these 4 integers. So in terms of words, it says that if 2a is a sum of squares of 4 integers, then you can also write a as a sum of squares of 4 integers. That is the meaning of that. Let us see how to arrive at this. Okay, let us take the given statement. 2a equal to sum of squares of 4 integers. So we have taken. Right. Now there are The left hand side is 2a, so it is even. So the right hand side must be even. And we know that square of odd number is odd, square of even number is odd. Therefore, for these x0, x1, x2, x3, now there are three possibilities. What are the possibilities? First one, either all these must be even, or two of them are even and two of them are odd, or all of them are odd. These are the only three possibilities. Whatever may be the possibility of these three cases, we can arrange them suitably, we can arrange these x's suitably, and we can pair them in such a manner that when you take these new numbers, x0 plus x1 by 2, x0 minus x1 by 2, x2 plus x3 by 2, x2 minus x3 by 2, these numbers are integers. It is always possible, whatever may be the possibilities, three possibilities, it is always possible to renumber and group them so that we can get all these as integers. We take these new integers as y0, y1, y2, y3. Okay. Now when we take the squares of these new four integers, it is a very simple algebraic calculation. When you calculate, you get half of x0 square, etc. This x0 square, x1 square plus x2 square, x3 square is given in the claim as 2a, so you get a. So if you see from this side, a can be written as sum of squares of four integers. So if 2a is a sum of squares of four integers, a is a sum of squares of four integers. Thus we proved that claim. Okay. Now look at the what we already asserted. We already proved that 4p, this 4p is a sum of squares of four integers. Because 4p is a sum of square, by our claim, 2 into 2p is also a sum of four squares, which implies 2p is a sum of four squares. Because 2p is a sum of four squares, p is also a sum of squares of four integers. So finally we proved that the prime number p is the sum of squares of four integers. So you will have to remember what we started in the beginning, that when you look at this, see we started with this. We started that proof by saying we are going to prove for prime numbers. For prime, even prime we already proved. Then we took odd prime. Now for this odd prime also we proved that it is a sum of squares of four integers. So sum of squares of four integers. So when n is prime, the theorem is proved. Okay. Now if n is not prime, that means if n is composite, what happens? We know that every composite number can be uniquely written as a product of prime numbers. Product of prime numbers. And we have Lagrange's identity, which says that if you take a sum of squares of four integers, another sum of squares of four integers, when you multiply them, again you will get a sum of squares of four integers. Because every positive integer can be written as product of primes, by this Lagrange's identity, we can easily conclude that number product is also, composite number is also a sum of squares of four integers. In this manner, we have established that every positive integer can be written as a sum of four squares. Sum of four squares of four integers. So this Four Square Theorem is proved. I hope all of you understood this. Thank you for watching this video. Thank you.